So in this section, we're going to have a look at loops. We're going to start looking at ways in which we can use OpenMP to parallelize loops, which is one of the most powerful things that we can do with the OpenMP library and with threading. If you imagine we have an iteration and we want to use the power of threading to execute different steps through that iteration at different times, and this is the kind of bread and butter work of OpenMP. So let's start with a simple for loop. Non-parallelized, haven't even included the libraries. I equals 0, I less than 20, plus plus I, and print out what I is. Let's just compile that. And there we go, and we have I from 0 to 19 in order, no duplications, everything's fine, sequential execution. So now we say, okay, well that's great, but I've got 10 cores, so a very simple sort of calculation. Really, I want to execute this in parallel across the 10 cores, so I want it to be 10 jobs each of 2 execution cycles. Let's see and let's start parallelizing this now. So we include openmp.h, go into here, we put the for loop pragma, oops. Put this into a parallel region. Sometimes VS Code is too helpful for its own good. Okay. So we've created a parallel region. We've done exactly what we've seen before. Let's compile this. Remember to link OpenMP. Okay, let's kind of look. So what we can see is that we have indeed parallelized it, and what we've done is we've parallelized the for loop, not to make it more efficient, but what we're doing is each thread has executed that for loop in full. And we can see that a bit clearer if we say I equals D in thread D, and then here, oops, OMP get thread num. So you can see that it's each of the threads is executing the for loop fully in order to go through. So unsurprisingly, this is not what we want to happen. Now, there are approaches where we could start thinking, oh, well, we're quite clever, right? And we could get the OMP thread num and we could do some calculation to it. We could say, okay, if, you know, this divided by that has no remainder, so we know that it's within the number of executions, then only then execute this code and so on and so forth. But fundamentally, we are still executing this loop fully within the thread. And there is a much cleverer way to do it. So unsurprisingly, this was thought of when the language was constructed and built. And what we have is we have an extension to the OMP pragma. We can say pragma OMP parallel for. So this is a specific construct which is saying that the next item is a for loop. We can't have a control block. It needs to literally lead on to a for loop. So let's just space that back. So we're saying the next item, the next command structure is a for loop, and it has to be or else we'll get a compiler error. Execute that for loop in parallel, i.e. handle all of the complexity for me. Right. And so now when we go through, you can see that there's only values of I. Now, they're not necessarily happening in order. Remember, we don't guarantee order here. We have 10 threads, 0 to 9, and each of them is doing 2 pieces of work. So thread 1 is getting items 2 and 3. Thread 0, you can see it gets 0 and 1 down here, and so on until all of the iterations of the for loop, all 20 iterations, are divided by the 10 threads. Each thread gets 2 pieces of work. This is called static sharing, and later on, if you carry on, we will look at ways in which we can, you know, tell OMP how to handle scheduling, and there's lots of different approaches to it, but this is absolutely fine for the moment. we're saying we have 20 pieces of work, we want to divide them up equally between the threads, and each one gets 2 pieces. So now, just with this simple construct, we've taken a standard for loop, we add this, and that's all we need to do in order to parallelize it, to run across. And this is one of the most, as I mentioned, the most powerful options that you can use OMP for.